And then this amount of information which we are carrying, the amount of variation which is captured using principal component analysis, it might be a limitation somewhere else because we are only capturing 73% amount of the information. But the advantage of PCA here is it is speeding up your execution of your code. Okay. People generally use PCA only for reducing your computational time, for dimensional reduction techniques. It has never been implemented to reduce your accuracy or increase your accuracy. We cannot judge on that. Okay. And yesterday, that was the reason that I was slightly skeptical. How does the accuracy behaves? And now it is quite clear. Your accuracy depends on your data. What features are influencing your output? What input features are influencing your output? Okay. Anyways, this data was very small, so it was quite easy to understand. Now let's start with 12th week session, which is deep learning or neural networks. So one small disclaimer before we start with our 12th week session for introduction to ML and AI using Python for mechanical aspirant. One disclaimer, this would be slightly complicated, and what I will be putting here, the points which I'll be putting in this week would only be serving as the base for your next course, okay, for your advanced course. Okay, so this will not influence your final project. This has nothing to play any role in your final project. But if you are able to do any project using this technique, which is neural network, it's well and good. If you're not, it's not a problem at all, because there is a complete course on this neural network which we'll be looking in our advanced course. But what I'm doing in this session is I'm just putting some base for that course. Okay, before going ahead, what I had asked some puzzle yesterday, were you able to get the answer? Okay, so I think I'll repeat this question, and then maybe what we can do, I'll quickly explain this. Okay, do you want me to explain, or shall I keep it as it is so that you can work on it? I'll quickly explain the question once again. So Naga, the question was, we all know that there is a chessboard. So the question was, there is a chessboard, right? And we know that the chessboard is of 8 by 8 most of the times. Not most of the times, like as per international rules, it should be 8 by 8. Now, if you notice, there will be some intersection points, right? So these are called vertices, and these are called vertices. These are called vertices, right? Vertices. So it's pretty clear that when you count this number of vertices, that would be 81 vertices. Now, with this 81 vertices, I have asked how many triangles can be formed. That was my question. Because we need, for triangle, we all know that we need 3 points. So how many triangles can be formed with this 81 points? I could have actually asked this question with 81 points also, but there is a slightly challenging task here which you need to think on those lines. 81C3 would be the total triangles, but many of these triangles would be actually lines. Exactly. So you got the logic right. But what is the right final solution? That you guys need to think, and then we can discuss that in our support sessions. Okay, I cannot form a triangle with these 3 points. So you got it right. So this is quite complicated. Think on this and then let me know the answer. Okay, so I will not be asking any puzzle for today, because I think you are already working on one puzzle, and then I have to keep some puzzles in the next course also, right? So before going into neural network, I want to explain few things once again on logistic regression in a different style now, into a different style. Let's say I have 4 input features. Now I am denoting these 4 input features as circles. The circles are called neurons. These are called neurons because neural network is the one which tries to replicate our mind, and our mind has, I don't remember the exact count, but it's in millions. You would be having millions of neurons in our mind, right? So if you want to do complete artificial intelligence with very high accuracy, we would need those many neurons to perform our analysis. But you can imagine how much computational time and how much computational efforts it would take. So if you remember, we had this x1, x2, x3, x4 as input features, and let's say we have the output as binary output. Okay, say 1 or 0. Okay, so let's say our output has 1 or 0. So what we have done, our all input features were going directly to our output. All the input features were trying to predict what could be the output, whether it is 1 or 0, right? So based on certain criteria, and then what was our logistic regression equation, if you remember? Let's denote this as Z now, because this would be useful in this session. And say, what was it? Beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4, right? And then we have used sigmoid function. I still remember the question which you have, why the sigmoid function is considered. The solution, is it because that sigmoid function ranges from 0 to 1? Is just because of that we are using this as probability? I still remember that. For that we have to wait for the advanced course, guys. Okay, so anyways, the sigmoid function is represented as probability, right? And that was this. So using this, we have done our logistic regression. These were the equations which we have used in our logistic regression. Okay, so far so good. Now let's say that this is my input x1. Please try to understand the terminologies and the figures. If you're not able to understand the math, it's okay, don't worry. We have a separate session on this. But for me, it's important that you understand the figures and the concept right now. So what do you think, what is the difference between these two graphs? Sorry, in these two diagrams or in these two figures? See, in logistic regression, we had input features. Using input features, we were able to predict whether the output is, whether it's for binary classification, whether it was 1 or 0, right? And then for predicting, each one of this would have some weights. Okay, ideally these all will have some weights. So this is how our mind also works. Neurons, and then from neuron, using synapses, you can look into this graph, this plot in Google, dendrite. How does dendrite works? Okay, so you can look into this figure in Google, but then there has to be some information which needs to be carried out from neuron, right? So that it tells what could be our output, whether it is 1 or 0, right? And that is what, if I want to convert my logistic regression equation, those are called as weights. This beta 1 would be now W1. This, I am just changing the terminologies now. Understand this. And this is denoted as B, bias. So now weights and bias, I'm just writing in a simpler form. And then this would be substituted into your sigmoid function. Did you understand? Okay, don't worry about the left figure. Did you understand the right figure? And the equation, what I'm trying to do? So far so good. I'm just converting beta into W1s. So those are weights. So it carries the information from neurons to output. Based on that information only, like in our mind also, there are synapses which carries the information. Okay, so that is how we predict. Like for example, if you see two fruits, apple and banana, in your mind, how would you know this is apple and this is banana? Because in our childhood we have been trained like that, that when we see apple, we know that our brain works in that direction. We call that as an apple, and banana as banana, because that is how our mind has been trained, right? But just imagine, this is very simple algorithm, which is logistic regression. Did you ever remember in your you have called banana as let's say watermelon, or let's say mango, in your childhood days, because you don't have enough knowledge, right? You are not yet trained. your parents might have told that this is apple, this is banana, but it's very difficult to recollect that, right? So how do we get trained that this is apple and this is banana? Again and again, we used to get trained by parents, right? Again and again, we used to get corrected. Again and again, we used to get trained. So what I'm trying to tell here is, here in logistic regression, you have trained only once. Just assume in that way. But here, when I'm putting an extra layer, this is called as hidden layer in neural network. So in this case, what happens, from x1, the information is being carried from all the x1, x2, x3 and x4, and from x1 also it will carry to other neuron also. So this might look very complicated. Okay, so what I'm trying to do here is, with the help of hidden layer, I am trying to correct myself in between one more time. I'm trying to get trained one more time using this hidden layer. Before predicting the output, I'm just trying to predict few more intermediate points, and we will check whether those points are correct or not, and based on that, then we will predict what is our output. Did you understand this analogy what I have given with respect to fruits and this one hidden layer? What we are trying to do here is, we are trying to get correct, we are just getting corrected one more time. Think in this way. Did you both understand this? I know it's quite complicated, but I'm just trying to give you some analogies based on this. Okay, one more thing. It's not necessary that hidden layer should have less number of neurons in comparison to your number of input neurons. It's not necessary, okay? It can have equal also. Let's say this is your x1, this is your x2, this is your x3, this is your x4. So these are our weights. Yes, now you have a right point. So imagine that for this 4 points with this weights W11, W21, W31, W41, say you are using logistic regression and you are achieving this point. Okay, now with this different weights, you are getting another logistic regression, and you're using another logistic regression here. And with this new data points, say here you have now your x1, x2, x3 and x4. Using x1, x2 and x3, x4 with these different weights, we are coming up with new inputs, or let's say these are the outputs for your x1, x2 and x3, x4 based on different weights. Okay, these are the outputs: A1, A2 and A3. No, you don't decide the weights. So before, okay, so, and then using A1, A2, A3, now this would be considered as your input to your final output. Okay, so what we are doing here with this weights, first we calculate Z here, And you remember the formula for z, right? Wx plus b, all those coefficients. Using this z, then we calculate this a1. How do we calculate? By sigmoid of z, which is 1 by 1 plus e power minus z. Here it will be z1, here it will be z2, here it will be z3. So similarly, I will calculate a2 and a3. Okay. Now, I'll just tell your answer on this, how do we decide weights, and then the detailed thing of deciding the weights will be in the next course anyways. I'll just quickly tell you. Do you remember in linear regression, how did we decide these values? Beta 1 and beta naught and beta 1. Let's take this same analogy with Wx plus b. Take the same analogy with Wx plus b. Do you remember how did we evaluate this beta naught and beta 1 in our linear regression? Yes, that learning rate, right? So we have to minimize our error. Based on using gradient descent, we have come up with beta naught and beta 1, right? So similarly, here also we will minimize our loss function. So in this case, what would be the loss function? I'm using logistic regression here, so it will be loss function would be the logistic regression loss function. And we haven't discussed the loss function for logistic regression. I've just told you that log loss, the loss function for the logistic regression can be calculated using log loss. Okay, so just remember that. Don't worry how do we calculate now, but I'm just trying to give you mathematical intuition that these weights are also calculated by reducing the error. Okay, so now if I try to explain this, how do we calculate and all, it would be really difficult because this requires the knowledge of derivatives. The way we have done in linear regression, we have to do the same thing here. Do you remember how we have done it? We have calculated the derivatives and then we have updated our beta naught and beta 1. Similarly, we have to calculate the derivatives and then we have to keep updating our weights. Okay. But then if I go into more detail now, there are high chances that you might get confused because this is just a opening. I'm just trying to put some base for your next course. Okay. But there is one thing which I can tell you now is why I am using this activation function. So this A1 are called as activation functions. So in this course, you have to remember all the terminologies which I'm using. Okay. Activation function 1, activation function 2, activation function 3. Okay. And how do we decide how many neurons we need? It is again hyperparameter. Do you remember what is hyperparameter? For random forest, what was the hyperparameter, guys? By changing the parameter, your accuracy also changes, right? So number of trees. Similarly, what was the hyperparameter for linear regression? What was the hyperparameter for linear regression? Learning rate, exactly. Similarly, deciding the number of neurons in your intermediate layer, which is called as hidden layer, is also a hyperparameter. So this will not be coming in straightforward. You have to decide how many of these hyperparameters are required. And this can only be achieved by trial and error. And once you do a lot of projects, then only you will come to know how many neurons should I use. But that is, hyperparameter is generally trial and error, right? So now this is our activation function. Okay. Now just assume that, okay, before going that. So I'm using this activation function here as sigmoid function. Okay. So there are different types of activation functions in neural network. But let's only think as of now with sigmoid function because I don't want to confuse you. Okay, so one thing is from the input features, you predict something which are called as intermediate hidden layers. From hidden layers, you're predicting your final output. And in your hidden layers, you calculate this z values, which is wx plus b, and then you calculate activation function, right? And based on this activation function, again it goes here, and then what it does, it's very important that you understand this very simple architecture of neural network, which I'm trying to explain you. Let's say there are weights, okay? I don't want to put those lines now. Okay, try to follow this. Okay, guys? Can you tell me what does this indicates? This superscript 0, 1, and 2? Like, what do you think what this could be? Superscripts? Exactly, those are layers. And we always called input features as 0th layer. This is our intermediate first layer, which is hidden layer. So this is first layer, and this is our second layer. Okay.